Hi! Today we'll be taking a look on how to build an EEPROM programmer, a very simple EEPROM programmer. And there are a lot of ways to do it, and I think a very simple one is to use an Arduino and interface it with the EEPROM. And for that we will also be using some shift registers that will add some extra ports to our Arduino, transform one port in one serial output in a parallel output using the shift registers. I will explain that in a moment. And why we would use a EEPROM for nowadays, a parallel EEPROM, since they're almost obsolete and have been substituted for serial EEPROMs. And the reason is they are very good to replace combinational logic in the way that they have some inputs, that is the address, and the output that is generally 8-bit output for 8-bit bus. And we transform this EEPROM in a lookup table. We program it with the output respective to the input from the address, and we put there what we want the output to be. So we can replace any combinational circuit with this limitation of 8 output and per chip, and depending on the memory size, also the inputs. Very common ones, this one for example, this is an Atmel 28C64. It has 12 address pins, and we also could use a 28C256, which has 14 address pins, or a 28C16, which has only 10 address pins, depending on what we need to do with our circuit. And of course we could also use 2 of them and address them the same, but then we would have double the output pins, 16 in this case, or use 3 in parallel, etc. So that's what we'll be building today. I'll show the schematics right now. The schematics for the EEPROM programmer I have drawn on a very unconventional way, because I thought it would be easier to explain, more or less. So I've segmented the schematics in some major parts, major functionalities, and the first one that I have built and will show is the connection between the Arduino and the I/O pins from the EEPROM for reading and writing data. And this is pretty straightforward. I just used the digital inputs from 6 to 13, and I have assigned all these pins the way it's connected here to the Arduino. The next part is the address part, and I have done this with the help of the 2 shift registers that will transform the serial data coming out from digital pin 2 of the Arduino into the full address width of the EEPROM. In this case I have represented here the 28C255. No, in this case I have used here the 28C256 because it's the same form factor. It just has 2 extra address pins, and in this way we can use our programmer to program an EEPROM from the 64 to the 256 from the 28C family. And the way this works is it receives the serial address from digital pin 2 of the Arduino into the serial input of the first shift register, and by each clock pulse that we'll see in a moment, it stores the bit in one register, and by the next clock pulse it shifts this bit to the next register and stores the one that came from the serial input on the first one. And so it shifts all the bits from the registers it has inside. This one has 8 registers, and the last one it sends to the second shift register, so that we can keep addressing all the pins of our EEPROM. So that's fairly straightforward. The connection is the serial input from the Arduino, then we connect pin 9 from one shift register to pin 14 of the second shift register, and connect all the address pins on the way I connected here, which is from the number 1, this QA, and up in this very order A0, A1 until A14. And this part of the schematic shows the controls we'll have to do to be able to work with the shift register. We have not only the serial data coming from pin 2 that I showed, we also have the clocks, and it used 2 different clock pulses. One of the clocks, which comes from pin 3, is the SR clock, and this one is the one that should pulse for every change in the serial data. It will then shift the bits inside the register. And the other clock that we also use, this R clock coming out from pin 4 of the Arduino, is the clock that it uses to latch this result we have into a second register inside the 74HC595. And the last control we have on these ICs is the clear. I've hooked it up to pin number 5 of the Arduino. And on the EEPROM side, we have to control 3 pins. One is the write enable pin, then the chip enable pin, and the output enable pin. The write enable, of course, we need to control if we want to write to the EEPROM, so that's fairly obvious. The output enable, it's important to control, because we not only want to write to the EEPROM, we also want to be able to read what we have programmed. And the last one is the chip enable. That is not mandatory, but I decided to do in order to maybe save some power. If we are not programming or reading from the EEPROM, it should be then on standby mode. And notice that I've used the analog ports of the Arduino, which is perfectly fine to do, because we can also use the functions, the digital write functions, directly on the analog ports. They will work just as well. And at last we have to hook, of course, power and ground to everything. And I've also grounded the output enable of the shift registers, because, well, it doesn't need to be controlled, since we already controlled the R clock. That is the second register it has inside the IC. And I've also added 2 LEDs for monitoring the activity of our programmer. And finally, we have here the full, very messy schematic but with color code, so it's a bit easier to understand and to get on to the soldering part. And we'll be building this into a perf board. I already cut it to size, and we'll keep the diagram more or less the same that I showed you on our schematic, and we'll just put the components in the perf board and then start soldering. But in the end, we'll get something more or less like this. And we'll be able to program the EEPROMs with it. After some hours of soldering again, we got our EEPROM programmer done, and we can stick the Arduino on its socket, and we're ready to start programming. The way I did the programming of our EEPROM programmer was to create a library, and this library will make it easier for us to use the programmer, because we only need to call the functions to write a byte or to read a byte, and also other activities, without having to complicate every code that we write that needs our programmer. So this library consists it starts here by assigning the pins that we used on the schematics. The write enable pin, for example, is connected to A0, the output enable to A1 from the Arduino, and etc. The control lines from the shift register and the LEDs, and the data pins that connect from the Arduino to the EEPROM. And another constant that we have here is this write cycle time equals 10. I will discuss more about this later on. So the second part of the library is this initialization, is the first function that we write, and it will simply start by assigning the pull-up resistors to important outputs, so to say, to avoid accidental operation. The write enable, the chip enable, and the output enable will be set with a pull-up register, so that from the beginning of the program nothing will be sent to these outputs. After that, we then finally do the pin assignments, and we set these same pins to outputs, and also the control of the shift register will be also always outputs, and the LEDs. And we call here this function set standby, and the set standby function will set the write enable pin high, so we won't write anything. We'll set the chip enable high, so we will also not select this chip, and output enable high. That should be enough already to put the EEPROM in standby mode, but I thought it would be also interesting to clear the shift register, and we do that by setting the clear pin high and then low, so just by pulsing this clear pin. But that's not enough to clear the shift register, because this clear pin is only connected to the shift register itself and not the output register within the chip. So we also have to pulse this output register clock here to clock in the zeros that we set on the shift register. And I can show you this on the schematics. What I said is this clear signal will only clear the shift register registers. Then we have all zeros here on the outputs, but the output register will still contain whatever it did on the beginning. So we have to just pulse our clock here and then clock in the zeros. And finally we have then reset or shift registers. Coming back here to the code, then we will clear the LED status and we will delay this 10 milliseconds that we decided to call write cycle time. Other functions that we have is the set read and set write. They're very similar. They will just set up the EEPROM for reading or writing by, for example, the read function will set the green LED high, we'll set the write enable pin high, we'll select the EEPROM and then enable its output, and also put the Arduino data pins into input mode, and also delay the 10 milliseconds. And for writing data is very similar. We'll set the red LED high, and then we'll not enable the output of the EEPROM, and we'll set the Arduino data pins as outputs. So we will output the data from the Arduino to the EEPROM. And we also wait here the 10 milliseconds. Now to the functions that deals with the shift register. We have this set address function that will put on the EEPROM address pins the address that we want, and we'll use the shift out function that is already from the Arduino library, and it works. It's a function that is already implemented to work with shift registers for 8-bit data, and since our address is 16 bits, we will have to use it twice, and we will have to pass to this function which pin is the serial data, which pin is the shift register clock, what is the direction of the data that we're sending. We say, well, we're sending the most significant bit first, and then the data. And since I said we are dealing with 16-bit addresses, the first, and we are doing the most significant bit first, so we have to shift the address right by 8 bits, so that we'll send the 8 most significant bit first, and on the second time we call the function, we can leave here the complete address and we'll just send the other 8 bits that were missing. And then we pulse the register clock. For reading the EEPROM, we'll use this address function that we wrote, and also we'll then acquire the data from the EEPROM using this function here, this loop that will read for each data pin on our data pin array and store on this data constant whatever it was present on the EEPROM output. The write EEPROM function is similar to the read EEPROM, in which we use the address function we wrote, and we also pass the data we want to write on the address. We set this data on the Arduino pins, and then we pulse the write enable pin. And the write enable pin was set to high on the standby. We just put it low and then high again. It would seem that this wouldn't work because we don't have any delay here on the program itself. But and we have a minimum pulse width that we have to keep for the EEPROM to write a bit to this address. And if we take a look at the data sheet from this EEPROM, this pulse width time is 100 nanoseconds or 0.1 microseconds. So we could have added to our code a delay microseconds. That's the shortest delay that we have on the Arduino library, and we could delay than 1 microsecond, which would be already 10 times larger than what we need according to the datasheet. But as it happens, we don't need to do this. I have uploaded a video in which I test the Arduino switching capabilities, and if you want you can watch this video. I'll leave it here on the description. And I show it there that the fastest an Arduino Nano can switch its outputs using this digital write function is 6.8 microseconds. So no need to add this 1 microsecond delay. He wouldn't do anything to the code. Maybe it would, because we have a longer code than the one I used to test it. But the fact is, we are 6.8 microseconds is already 68 times longer than we need as per the datasheet to write a byte to this address. So it's fine. If we just leave it like it is, it will work just fine. And then we have here this delay write cycle time, that we have the constant of 10, which we will translate here to this delay is in milliseconds, 10 milliseconds, and we have to wait this time between switching the address on the EEPROM. And why is that? Well, if we go back to the data sheet of the EEPROM, we see here on the next page here the page mode characteristics that we have a write cycle time of 10 milliseconds maximum if we want to keep writing on this page mode, and we actually want to avoid that for now. We just want to sequentially write the bits, so we have to wait this 10 milliseconds, or else we will be going into this page write mode, which is a bit more complicated. And I just want to keep the code simple for now. It's already fast enough. You'll see when we program the EEPROM. It's already working fine. So we'll just wait the 10 milliseconds. And that's also why I have added this delay on each of the setup functions, the set standby, set write, and set read. So we would avoid entering the page writing mode on the beginning of a writing. And that's almost it for this library. We also have here a extra function which prints the contents of the EEPROM. It's a dump function. It reads all bits from the EEPROM and organizes it for show, showing the addresses as integers, and then the data as hexadecimals, just for keeping it a bit compact and so that we can better see it on the terminal. And we also have a erase all, which is simply calling the write function, and then for all addresses while writing the 0xFF or 255 in integer, or all ones in binary. So that's it for this library, and I'll see you on the next video where we'll finally program the decoder or binary to decimal decoder. Hope you enjoy it.